It's time to get into networking. Networking in cloud is pretty wild. It functions very differently than our traditional networks. And in security, a lot of us come from networking backgrounds, and it can be really hard to wrap our brains around how cloud networking is different and understanding the security advantages that that gives us. What we're going to do today is I'm going to spend a bunch of time talking about networking. I'm going to give you a brief overview, a little bit of background about regular networks, and then we're going to get into cloud networks. And the only reason I'm going to cover the regular networking stuff is I don't assume all of you understand why networks work or how they work. And I'm not going to get into the details, but I am going to focus on the key points that are different in cloud so that we all have a baseline understanding. Let's go to the whiteboard. This is kind of a mock-up of a very simple one of what a network could look like. And networks really have three kind of major components to them. First is the endpoints. Those are the things that are going to send out and receive the traffic on the network that are talking to each other. Then we have all the switching and routing hardware. That's what determines how something gets from a communication from point A to point B or point C. And then we have the physical wires that are connecting these things together. Here's really how everything kind of works today. The networks we use are what's known as packet switch networks. What does that mean? Well, fundamentally, we communicate using packets. A packet is a small bit of data, and that data has a header associated with it. And there's some more information in this on the header, but the simplified version is it's the source, where did it come from, where is it going, and over what port and or what protocol. What are ports and protocols? Well, imagine we have something sitting over here, and maybe it's a web server, and then it also has something called SSH running on it, and then maybe it also has email on it. Those are all different applications. And the server, the computer itself, needs to know which application gets which networking traffic. And that's what we use for a port. So the web server is listening for traffic on port 80, and the SSH server is listening for traffic on port 22, and the email, it depends on which kind of email protocol you're running. And that's also what the protocol is. You all are very familiar with HTTP because HTTP is the protocol that all web runs off of. SSH, it's both the service and the protocol itself. So how does a packet switch network work? Well, this computer will send a packet through a network interface, that's the little hardware thing on the computer itself, to a switch or maybe into a router. And look, I am oversimplifying things a lot and possibly making them more complex, but it works for our purposes. That switch or that router is going to read that header, and it's going to say, oh, this thing wants to talk to this thing. Who owns that destination address? What we use today, we tend to use IP addresses because we use something known as IPv4 is the protocol that we use to send these packets around. And within IPv4, an address will look something like this, 10.0.5.4. And you've probably all are familiar with looking at IP addresses. By the way, there's also IPv6, and once I figure it out, I'll explain it. Now, I know kind of how it works, but we're not going to get into that because most of what we're using is still that IP version 4. So let's suppose that that's the destination address. And so this piece of hardware, it's going to have software running on it, and it's going to kind of say, oh, well, who kind of owns the, I don't know, the 10.0.0.0 network? Oh, I own that network. So it's going to send that packet over there. And then it's going to go, oh, who owns the 10.0.0.5.0 subnet? Well, this one over here, I own that subnet. So it's going to route that packet over there. And then it's going to go, who owns that IP address? And then that's going to say, I own that IP address. And that's going to route it all there. And that's kind of how it works. All of these packets are dumped onto these wires, and they are moving around the network, advertising, here's who I am, here's where I want to go. Well, this creates some kind of security issues that we are kind of used to dealing with as information security professionals on the networking side. So I cleaned it up a little bit. And what are some of those issues? Well, if a packet is dumped onto a subnet, for example, if it is, let's say it's dumped here. Suppose that there's a bad guy who manages to connect to that network here. They can kind of listen to that traffic, potentially. They could potentially intercept that traffic. Now, we have a lot of things to help protect us, including the ever famous firewall, where the firewall will say only allow traffic through that meets certain rules. But without something like a firewall that says, I'm only going to let port 22 traffic go to 10.0.5.4. Actually, that'd be a bad rule, but let's suppose it has it. Without something enforcing those rules that isn't actually built into our networks, anything can talk to anything else on that network. So that's an important point to understand. Any one of the additional things connected here, they can all talk to anything else on that network, and the rules get enforced only by us adding in that additional hardware, the firewall, to make those decisions. Now, that was firewall. Set my scope different on my little tablet here versus what's on the screen. The other thing is these bad guys, they can also like try and spoof and send fake traffic onto the network because they can just dump everything out from their network interface and see what happens. There's lots of tools and stuff we use. This all works on wireless networks as well. And that's fundamentally how these networks work. Now, how does the internet work? Well, this whole network might have these addresses here. So this 10.0.0.0, and I'm going to put a /16 on. That'll make sense someday. That is not routable over the internet. That's like a bunch of addresses that everybody reuses and can use on their local networks. But you're going to have some kind of a gateway, and it's usually a router that has one IP address that is internet accessible. And I'm not going to write one out because I'll probably get it wrong, but there's one in the blog post with this. And then that connects to the internet. And the internet is just a connection of a lot of networks that all speak the same protocols. And it all uses a global address space. So every one of these gateway thingies on the internet has a unique IP address. And in some cases, individual devices can also have their unique globally routable IP address. As a matter of fact, all the IPv6s are unique around the world and can route everywhere. All right. That's a super basic view of a packet switch network. The thing to remember is we're taking these packets, we dump them onto the network, and all of the routing and switching hardware figures out how to get a packet from point A to point B based on the addresses. Well, let's shift gears and let's talk about how Amazon does things. And we're going back over to the whiteboard to go through that. Important thing to remember is that Amazon and almost all cloud providers use a concept known as software-defined networking. Let's go back up actually to our earlier example here. As you might imagine, I talked about the concept of a subnet. Actually, I'm going to go into a little white space over here to describe this. And the concept of the subnet is here's a bit of a network with a bunch of things on it. And all of those things on that network, they might be 1.0.0.5.4, and this one might be 5.3. They're all part of this kind of same subnet. We have divided up our network into smaller pieces, and that handles all of the routing. And so on this bigger network, it knows that anything with that .5, 10.0.5 is controlled by, is in this physical part of the network. Well, what if I'm in an environment where I want to have, for example, a resource in this corner of the data center and a resource in this corner of the data center, and they're both connected to different pieces, different switches, different routing hardware, but I want them to act as if they're on the same subnet. That's really hard for us to do. And that's just not how we have architected and built our networks. Well, let's go back over to Amazon and talk a little bit about some of the problems they have to deal with. One is Amazon needs to support networking so that cloud customers that already have IP addresses and already have stuff in their own networks, they want to be able to connect those into Amazon and use Amazon to expand their data center. The only way to do that is if Amazon can allow them to use whatever IP address ranges they want, even if another customer wants those. Amazon also has to operate on massive scale. So imagine that problem, but if 1 million customers all want 10.0.5.4, they need to be able to provide 10.0.5.4 to a million customers. Wouldn't surprise me if they already have a million or more customers using that IP address today. And also, a customer's resources might be deployed in all sorts of different parts of Amazon's infrastructure. But if I build a subnet, I still want all of those things to be able to talk to each other. So the way that Amazon handles this is through software-defined networking, which Azure and even maybe your Office network uses as well, where it abstracts out the network and it uses kind of virtualization. What software-defined networks do is they decouple the management plane from the data plane. So all the control, all the management is run in software, and then it dumps it onto the physical network to route things around. This will make more sense as I explain how it works and the implications of it. So we're going back to the whiteboard. So let me move my whiteboard over here, and I'm going to set up the problem first. Let me zoom out a little bit here if I can, and then we're going to walk through it. So following my little mouse on the whiteboard, imagine that we have two different customers, red and blue, and each customer has their own VPC. VPC stands for Virtual Private Cloud. A VPC is basically the virtual network that you run in AWS, and you can have a lot of them. Not as many as you want per account. Well, as many as you want if you have a lot of accounts. I know organizations with many thousands of VPCs. I own myself hundreds of these things, hundreds of virtual networks. So let's imagine that I'm this VPC red customer, and my VPC has an ID of 456, and its IP address range is that 10 IP address range, and that /16 is a notation that says, yep, this is a network of a certain size. And we're going to go into, it's called CIDR, CIDR notations. We'll get into that pretty quickly, but I'm not going to go into detail today. But a different customer, blue, has VPC with their ID of 123, and they want the same IP address range. At the same time, Amazon has to run a physical network still, and their physical network, over here, they still have a server with that IP address on the physical network. And so if I have something here, 10.0.5.1, it's an instance, which is a virtual machine, and it wants to talk to the thing that owns 10.0.5.4, but only on my network, my VPC, and some other customer is also using that address on the same physical server, which is different than the address of where this is. This all could be very confusing. And Amazon solves this elegantly with software-defined network and virtualization. Let's go through the process. So let me change my colors here. So I've got one that's going to show a little bit better as I walk through this. There we go. Make that a little bit brighter. Okay. Let's imagine that this server here wants to talk to this one over here, which is what I had originally described. Every server, your phone has a network interface on it. The network interface is the hardware that connects you to the network, to the wires or to the wireless. Well, in this case, the network interface, I'll put it right here, it's virtual. And it's software that is just run in the virtualization software that runs on Amazon's physical server. Actually, it's hardware. If you're running on Nitro, we'll get into that later. It's called an ENI, which means it's an elastic network interface. So an ENI is different than the physical hardware that would be installed onto the server itself. When I send that packet out through my elastic network interface, Amazon will take that packet and it wraps it. And what it does is it will put it inside of a wrapper. And the first part of that, and again, I'm simplifying and I'm bastardizing this, there is a wonderful presentation called A Day in the Life of a Billion Packets given by Amazon engineers. It's linked in the blog post. I really strongly recommend you go watch that if you have a networking background. But this is my simplified interpretation of it. So that server says, all right, this thing on this VPC wants to talk to this thing on this other VPC. And that's kind of what I've shown here. So the source VPC is 456, the source instance ID, and technically I think it runs off of the ENIs, not the instance IDs, but I already wrote instance IDs because it's easier to think in those terms. And it's this IP address, and then it wants to go to this one. But it's that full string. It is which network, which actual virtual private cloud VPC is it on, and what's the source and what's that destination. That server then goes, all right, I know what the user is requesting. They want to talk to 10.0.5.4 on this VPC. First thing I'm going to do is I'm going to check with something called the mapping service. And that's this big database thingy or whatever it is that Amazon has that keeps track of all of these assignments. And it says, hey, this instance over here wants to talk to this instance over here. Is that allowed? And where is that other instance on the network? Might be on the same server. Who knows? The mapping service says, well, in this case, it is approved, and you're going to want to send it to the physical server of 192.168.7.2 over here. Great. That's added to the wrapper, and then the hardware and software on that server then sends it out onto the network itself. Whatever Amazon uses for their internal networking functions there, and it gets to the other side. And the first thing is the other side checks. It says, hey, is this allowed? Should I be expecting this packet? And that's cool. And that's very different than our regular packet switch networks. Because like without a firewall, you're never checking to see if something is allowed or not. It's just moving on the network. And so it checks, and the mapping service in this case says it's approved. Send it to this instance. That packet is then unwrapped, sent to the network interface of that receiving instance. So very different. Like Amazon can send these packets all over the place. They actually can create other kinds of software constructs we're going to get into for communicating to the internet, for network address translation. They can fake different parts of the network. It's just all running in their software stack. You have to still have the physical hardware. You still have the boxes and the wires. It's just that Amazon is wrapping the packets up and just creating a network on top of a network. They're creating millions of networks on top of the one big physical network. Again, work with me on some of my scale and stuff. Amazon friends, don't get too upset about my description. So this is really wild in a couple of different ways, but there's one kind of core that matters. And going back to the whiteboard here. In a packet switch network, by default, anything can talk to anything. So as long as the addresses don't conflict, there's really no reason, there's nothing that's going to necessarily stop it. The other is anybody on that network, if they're physically in the path, they can potentially listen to that traffic. And the way to think about a packet switch network is you've got all these packets floating around all over the place. They're all dumped onto that network wire, and everybody just is listening. And I don't even know how to draw a picture of an ear, so I'm not going to. And they're listening for packets that are destined for them. So it's just all floating around out there. It's one big kind of mesh on that network. Well, let's think about what Amazon's network does. Because in this case, you have a source and you have a destination. And yeah, Amazon has its under the waterline network. That's, what they've used to actually build all of this out. But fundamentally, the source thing gets wrapped up and it's sent straight to the destination. And even if I have another instance, another virtual machine on the same network, it's never going to see it because Amazon only unwraps that packet and sends it to the specific destination that's expected. So even if I have another red, so let's say this red over here on the left side, if I want to listen into the network, I can't listen into the network. I can't fake my traffic because Amazon got the big database of who owns what IP addresses. Like, I'm stumped from as an attacker from a security standpoint. And that's what I really love about networking in AWS. A friend of mine, James Arlen, years ago, we are teaching at Black Hat together. And I'm describing this. I'm doing the talk very similar to how I'm doing it here with the bad drawings and everything. And Jamie goes, oh, yeah. So basically, we've taken a packet switch network and turned it into a circuit switch network. It's like a game of telephone. It's as if we had a wire from point A to point B, and nothing in between is going to look at that traffic or can modify that traffic. That is a profound difference from a packet switch network. It gets rid of a lot of attack paths and sniffing and spoofing traffic and faking traffic. And fundamentally, the network is also default deny. Nothing can talk to anything else unless it has permission. And once we get into security groups, you'll learn that that permission includes exactly which ports and protocols. Again, fundamentally different from a regular network where everything can talk to everything. In cloud networking, specifically in Amazon's networking, only if a source and a destination are allowed to talk to each other based on the management rules of the network are they going to be allowed to talk to each other. This is a lot of information. When I first started working in cloud, the first time I saw how some of this works, and actually it was a different networking architecture at the time, it really profoundly changed how I think about my network architectures and my application architectures. The way we're going to cover this is I'm going to build it piece by piece from the ground up and show you all the little intricate pieces, the primitives that we use to build a network. And we're going to slowly build out a network by hand. We're not going to use any of the wizards. We're going to do everything manually so you have a better understanding of how those pieces work. Then we're going to get into more of the advanced concepts. And then you're going to learn that there's even other overlays of networks on top of these networks, where you get into all of that as well. So I'm not sure how far we're going to take it on this first batch of labs, but with that, why don't we jump in? And today we're going to look at the network that's already deployed in your account. It turns out you have VPCs running in every region of every one of your accounts already. You're not paying a dime for them because there's no network traffic. It's just that software, those database entries are there for you to, if you want to deploy something, for that to actually work and for those to communicate. We're going to walk through those. We're going to see the different pieces this week. We're going to focus on a few components. And then next time, we're going to start building them out. We're going to jump into our test account that we had previously created, and we're going to look at the network there, just orient ourselves today. Because the lecture is a little bit longer, I'm keeping the lab a little bit shorter. So let's go down to test account, and we're going to use let's do administrator access, because at the end, we're actually going to delete that VPC so we can create a new one from scratch starting in our next labs. Okay, from the main page here, you see VPC comes up on my console, but just in case it doesn't come up on yours, let's go ahead and type that in. We're not going to talk about everything in the VPC, but we are going to focus on the key points. So you'll notice this is actually showing me what resources I have in the current region. This is a change that AWS made. I don't know when they made it, within the last year or so. I really actually like it because if I click See All Regions, you can see it's actually pulling VPCs in any of the supported regions. Why do we have unsupported here? Because those are regions or region not opted in. Remember, we have our service control policy that blocks everything except US East and US West. So the service control policy here is working, and I can only see the regions where I actually have anything up and running. So let's walk through what a VPC is, and then we're going to walk through the major primitives, the major components that build out a VPC. So the first thing is the VPC itself. And you can see that IP address range. And so that's a /16, which is what we call a Class B network, and it has 65,000 some odd IP addresses in it. So let's go ahead and we'll click on the VPC itself, and we pull up all of the data here. So there's a few things. Remember, we talked about those VPC IDs. That's what a VPC ID looks like. These are all unique. Remember, they're unique per region, and you might have overlap potentially if these things are in other regions. There's also something known as, is it a default VPC? What's a default VPC? Well, a default VPC is a VPC that if you go send a command to run anything, by default, it connects to that VPC. VPCs have their own route tables, and we'll go into what those are in a moment. Now, what's really cool is this is relatively newer in AWS. They actually give you a resource map. So the virtual network itself is the VPC. It's just this software construct that says anything with this tag in it is this VPC. I can click on it, and I've got all of that's what I'm looking at up here. This VPC has 4 different subnets, and I can actually look at these different subnets. We'll look at them in more detail in a minute. So the 4 subnets you'll notice are they have these little tags on them, 2A, 2B, 2C, 2D. What's that? This is known as an availability zone. Availability zones are like data centers within data centers. And availability zones are designed for resiliency. These are all separated out so that they're using different power, different like network connections, interconnects, so that if one availability zone goes down, anything running in the other one can still be running. But all of these are close to each other physically, and they all have high-speed networking so that availability zones can talk to each other. They don't have to go out on the bigger internet any further than that. You pay less for traffic communicating between availability zones. You'll notice all of these subnets are sharing one route table, which we're going to look like, and they have one network connection to other networks. In this case, it's known as an internet gateway, an IGW. Now, this is great because for years I was teaching and I couldn't show any of this visually. I had to draw out the maps. Now Amazon's doing it for me. All right, so we have our network. We have our IP address range for the network. DHCP has to deal with addressing and such. The route table is where do I route my traffic through? And the ACLs, we're not going to use ACLs for a long time. That's access control list. It is a network security function, but it's one that I typically recommend you don't use. So we have our resource map here. And if I want to see my address ranges, I can look at the CIDR ranges. That's here. Flow logs is for logging, and then tags and any other integrations, which are things that we're not doing right now. So from here, let's just go into one of these subnets. Now, these are all going to be identical. But notice this is the /16 address, so we've got that in mind. And then this one is a /20. So a /20 is, let me pause because I don't remember offhand. Okay, a /20 is about 4,000 IP addresses. You'll notice that all of those are in 172.3.1.32. My bigger is 172.3.1.0.0. So every one of my IP addresses is all of those 65,000 are going to be in that subsection there. That's how that addressing works. We do have to get used to working with it. This one is 3.1.3.2. This one's 3.1.16. This one is 3.1.0 with the /20. So this is how all of these are divided up into their own networks. And I have a lot of space for a lot more IP addresses that I could potentially add there. All right. So let me go ahead and blow into one of these subnets, pops it up as a separate tab. You can see this for yourself. Oh, and look, I didn't even have to do the math. It shows me how many are available. If I had things deployed on here, that number would go down. So I think that shows me, the number that are available. It shows me what VPC I'm in. It shows me what availability zone that I'm in. By the way, availability zones, this label of 2A versus 2B, C, D, it's kind of like a little bit different every time. And that just has to do with how Amazon works it. So your 2A may not be the same as my 2A. Don't just assume those things can talk to each other. We also have our account ID for who owns this subnet. So a lot of really good information. Well, what defines a subnet? It's that range of IP addresses. It's that CIDR range, which it's the whatever /20. I'm looking at too much at once. Here we go. And that's what's going to define that IP address ranges. Now, how do things know what other things to talk about? How do they route that traffic? Well, that's via the route tables. And we have 2 entries into this route table. And this is very, very meaningful. So by default, anything that starts with a 172.3.1, IP address is considered local. And that means it's going to be routed on this local virtual network. Now remember, the rules of the mapping service are, it's not that the traffic just dumps onto that network. It's going to go from a source to a destination, but it routing that packet, it's keeping it within this virtual network. Now what's this? That notation means the internet. That's the internet at large. So that's just the shorthand we use to cover the rest of the world. And if traffic is routed to the rest of the world, it's going to something called an internet gateway. And this is a software construct I didn't cover in my little lecture piece because we're going to get into it a little bit later. But this is like a thing in AWS that says, oh, if you want to talk to the internet across all of my massive IP addresses, I have to have software to manage that connections to the rest of the world. Because the mapping service doesn't know that, doesn't manage Google's IP addresses. So the internet gateway is control of sending those packets out And if you actually monitored that traffic, you send it to a destination that you own, you would see that you don't even always control what that IP address is. It could come from different IP addresses all the time, even for the same subnet. And it's going to take that traffic from the internet gateway knows, oh, this is coming back and needs to be routed to this specific thing that sent that traffic out. So there's a lot of brains in that internet gateway because it has to handle all those communications to the outside world and then make sure those packets go back into Amazon's software-defined network to the destination that they're supposed to go into. And as we get more into internet connectivity, we're going to cover internet gateways and NAT gateways. That's fundamentally how that works. Now, here's a cool thing because I have read enough networking route tables from AWS. I know that this is what we call a public subnet. What does that mean? This subnet has internet access, and I could deploy instances on this subnet that have a public IP address, and then I could connect to it from my home. It would allow that because that's what an internet gateway does. So anything that connects directly to an internet gateway can potentially be accessible on the internet. So I'll have to assign that out and work with it, but that's the way it works. Now, the network ACLs, these are security rules, and you'll see that the rule is allow all traffic and then deny everything else. This is just the way ACLs work. They're not stateful. They're not worth talking about at this point. We will get into them later. We're not going to use ACLs for what we're associated with. The core components that I am just focused on today, because we're being laser focused on keeping things simple, is the VPC defines the virtual network, the subnets, which is the different network components where I can deploy my stuff, and the route tables, which defines where do the packets go. That's those rules for what's allowed to talk to what at that subnet level. And then the network connections, which is how am I connected to the outside world through that internet gateway. Makes sense? It's going to make a lot more sense. We're going to build it next week. And to build one next week, we're going to delete our VPC right now. I don't like default VPCs. I like building my own networks. Every one of these subnets uses that same route table, which means they all have internet access. I don't have any private networking. So I'm going to we're going to hit delete VPC. And it's going to delete all of the subnets. You notice the subnets and the internet gateways are all going to be deleted out. And then it's a default VPC, so it's going to give me an extra little confirmation. So yes on the checkbox, and then yes, delete default VPC. By the way, what's the problem with default VPCs? Imagine I'm an attacker and I get the API. I managed to figure out how to run an instance in your environment. If I don't know where to run that, it's just going to default run on the default VPC and I can deploy my crypto miner. If I don't have a default VPC in the API call to run an instance, I would have to specify the VPC ID. The attacker might not know that. They might not have permissions. Anyway, there's a lot of reasons. You don't really need, I skipped that. I guess I hit the back button there. You don't really need to have your default VPCs. So let's get rid of it. Delete default VPC. And it's going to run through the process of deleting all of the pieces. Our default VPC is gone. All right. This was just to get us started. And a lot of these are complex things that I can't always simplify completely the first time around. What we've done is we've taken a quick look at an overview of how VPC works with the mapping service. And remember that it's all about taking that packet switch network and it kind of functions more. It's not a circuit switch network. It just kind of acts a little bit more like a circuit switch network. Then we looked at our constructs, which is the VPCs and the subnets and the route tables and the internet gateways. Just to give us the basics of the core components of any VPC is going to have those four pieces. Although you could actually delete the internet gateway, then you just can't talk to anything. And only things on that network can talk to each other is something that you can do. We're going to come back. We're actually going to build all of this from scratch, and hopefully it'll help it make more sense as we go further down that pathway. Have a great week.